Hi everyone. In the previous lectures, I had discussed about input offset voltages and output offset voltages of instrumentation amplifier. But I felt I rushed through the analysis and I thought I'll spend a bit more time on the offset voltages. And that is the problem we are interested in is how to find the input offset voltage of an instrumentation amplifier. Okay, given we know that schematic of the instrumentation amplifier, which comprises of 3 op amps and resistors. So how do you find the input offset voltages, and what is the goal of this analysis is that, let's say you are a circuit designer who is building an instrumentation amplifier, then it is of interest to know which op-amps here in the instrumentation amplifier schematic contributes maximally to the input offset voltage. Then as a designer, maybe you will try to minimize offsets for that op-amp. Okay, and generally as a analytic, as a part of the instrumentation amplifier analysis, I felt we should do a proper analysis of offsets as well. So that's why another lecture for this. So how do you measure offsets? I have shown here instrumentation amplifier at a top level as a 3-terminal device, right? An instrumentation amplifier is a differential amplifier and with a differential input and a single-ended output. And so to measure the offsets, I'm going to ensure that the differential input voltage is 0. Okay, so here I've shown the input voltage sources with their source resistance. Here the differential source resistance is assumed to be Rs, and therefore I'm showing it as Rs by 2 and Rs by 2 on the two input terminals. Okay, so Rs by 2 is one half of the source impedance seen by the positive, and the other Rs by 2 here is the other half of the source resistance seen by the negative input terminals of the instrumentation amplifier. Now ideally, if you ensure that if you make sure that the input differential voltage is 0, the output is supposed to be exactly equal to 0. But because of the presence of offset voltages, the input bias currents of the op-amps in the circuit, the output voltage will be finite, which we are going to call it as VO offset. In this lecture, we will try to find analytically what does this VO offset depend upon. And to do that, how are we going to find that? We will apply the principle of superposition. We will assume only 1 or 2 op-amps at a time are contributing, and then contributing to the offset, and see the impact of it, and then sum the output voltages due to all the individual offset contributors. Okay, then once we have the output offset voltage, we can divide it by the gain of your VO offset divided by the gain G. G here is the gain of the instrumentation amplifier, to get the input referred offset of the instrumentation amplifier. Now before we go to the analysis, I'll just quickly refresh your knowledge. Instrumentation amplifier is a 2-stage amplifier. The first stage is a fully differential input, differential output amplifier. The second stage is a differential input, single-ended output amplifier, or a subtractor with a finite DC gain. And the DC gain of the subtractor is given by R4 by R3. We called it G2. And the first stage gain is given by 1 plus 2 RF by R. So that's what I have written here. So this is the gain of the second stage, V0 expressed in terms of VO2, VO1 and RF by R3. And this is the gain of the first stage, VO2 minus VO1, that's the differential output of the second stage, differential output of the first stage, expressed in terms of the input signal. Here V2 minus V1 is the differential input. So the overall gain is given by 1 plus 2 RF by R times R4 by R3, which we are writing it as G1 and G2 times V2 minus V1. So we will be expressing all our offset voltages, the gains that they see in terms of G1 and G2, or the overall gain G. So before we begin the analysis, again to quickly refresh your memory, for an op-amp we discussed the mainly 2 different sources which can cause offsets. One is we said that we can mathematically model the offset as a voltage at series to one of the terminals. And also we should, considering the input bias currents, that can be consumed due to BJTs. Since we said op amps are a pretty stable and a very old analog IC, and so even today a lot of op amps are BJT input based op amps, and so therefore since BJTs draw finite currents, we will have finite input base currents. So IB plus denotes the input base current flowing into the non-inverting terminal, and IB minus represents the input bias current flowing into the inverting input. So keeping this in mind, we will now apply the principle of superposition and include one source at a time and find out the output voltage due to that. So first we'll assume the input op amps A1 and A2. So both the offset voltages of these op amps, as we have written it as VOS2 and VOS1. So here I have not shown the source resistance, even if I assume source resistance to be present here in series with it. Since we have ignored every other source of offsets, like bias currents and all that. So no, there will be no current flowing through the input, and the voltage drop across the resistors will be 0. Source resistors will be 0, so I can ignore them. I can fully ignore them. Now, if you look at this circuit, this looks like your standard instrumentation amplifier with a differential input. The differential input at the input of the if you see this instrumentation amplifier here, at the input, the differential input appearing across it will simply be equal to VOS2 minus VOS1. So that is VOS2 and VOS1 are the input offset voltages of the two op amps. Okay, they are the input op amps. Now these guys, if you refer it to the output, they will see the entire gain of the differential of this instrumentation amplifier, right? They are just directly appearing at the input, so they will see the same entire differential gain. So the total output appearing at the total output offset voltage due to the op amps input offset voltages, the input op amps input offset voltages, is simply given by V0 is simply given by G being the differential gain times VOS2 minus VOS1. Okay, so this is the output offset voltage. I will call it VOS due to the input offset voltages of the two op amps. Next, we will include the bias currents of these two op amps and see the impact of these bias currents on the output offset voltage. So when we include the bias currents, again there are two bias currents. One is the bias current flowing into the inverting, and the other bias current flowing through the non-inverting terminal. So we will only consider for this analysis bias currents flowing into the non-inverting terminals. So this will be IB2 minus, and this plus, and this current will be IB1 plus. Now you can see this IB1 will flow through the source resistance, and the voltage drop at this point due to IB1 will be minus of IB1 plus times RS by 2, and the voltage due to IB2 plus will be minus of IB2 plus times RS by 2. Again, since we have two voltages appearing at the input terminals, we know that an instrumentation amplifier will only react to differential inputs. It's going to reject common mode inputs. So the differential input appearing across the input is simply given by you have to subtract V2 minus V1. So the input this terminal is what we call it as V2, and this is V1 here, V2 minus V1. So if you subtract the two, you will get this expression, IB1 minus IB2 plus into RS by 2. This will see the entire gain of the differential gain of your instrumentation amplifier. So that's why I have multiplied it by G to get the output offset voltage. Now to find the impact of the input bias currents in the non-inverting terminals, I'll assume the input bias currents at the non-inverting terminal to be 0. So there will be no drop across RS, and we have ignored every other non-ideality. So therefore there is no input offset voltages and all that. So in this case, now if you see the current IB1, which is the IB1 minus, which is the input bias current, that will flow through only RF. Okay, and why is that? Because op amp this is still treated as an ideal op amp. So if this node is at 0, this node will also be at 0 volts. This node will also be at 0 volts. It will just follow the virtual node. So this node will be at 0 volts. So no current will flow through this resistor. So any current that the op amp is drawing at the input port has to flow through only RF. So the path for IB minus will be like this. It will flow through. It will flow at the input of A1, and the path will be in this way. So this is the path. It will flow from the output of the op amp will supply that current, and it will flow through RF. The same thing happens here as well. The path will be this. The path for the current for the op amp A2 will also be the same. So the voltage drop across the lower resistor here will be, I'm assuming the direction of current to be in this way. It will be IB2 minus times RF. And similarly, the voltage drop across this resistor RF will be IB1 minus times RF. So VO21 minus VO1, that's the output differential or differential output voltage of the first stage. That you have to subtract these two voltages of RFs. Remember, I said that the overall voltage VO2 minus VO1 will depend upon the voltages of the three resistors, voltage drops of the three resistors in series. Okay, these three resistors. But since the voltage drop across the center resistor is 0, we can just subtract the voltage drop across the two RFs. If you do that, you will get IB2 minus IB1 with a minus sign times RF. This will now get amplified by the second stage gain, right? So this is the differential input appearing at the second stage input. That gets multiplied by the gain of R4 by R3, which we call G2. So this is the input output offset voltage due to the inverting terminal bias currents. So this is the overall input output offset voltage due to the first stage op amps. Okay, the op amps A1 and A2 in the differential pair, the differential input amplifier. So we have analyzed the offset voltage due to the input differential amplifiers. Okay, the input op amps in the instrumentation amplifier. The other source is the third op amp, which is the op amp in the I've written the overall output offset voltage due to the offsets and bias currents of the input op amps. I've just applied superposition. I've added up all the voltages. Here you can see the input offset voltages, the difference between the input offset voltages of the two op amps gets multiplied by G. Again, this one is the input bias current flowing into the non-inverting terminal. So I've forgotten to show RS here. So there will be RS by 2, and there will be RS by 2 here as well. So IB1 plus minus IB2 plus times RS by 2. That's the input differential voltage due to the bias currents at the non-inverting terminal, multiplied by the differential amplifier's gain, plus the bias currents flowing into the inverting terminals. Okay, this is the overall contribution. I just added up all the three voltages. That's it. Now once you know this, the next step is to find out the offset voltages due to the input offset voltage and bias currents of the second stage op amp, the op amp A3 here. So again, we'll apply the same principles of superposition. First, we'll assume the only offset is present. I can model the entire offset at the input of the op amp. So here, remember, the way in which we are measuring input offset voltage is by ensuring that the input differential input is 0. If the differential input is 0, which means V2 minus V1 is 0, VO2 minus VO1 is also 0. Ideally, if you ignore all the input offset voltages due to the input op amps, then VO2 minus VO1 is also 0. Okay, since individually we are making VD itself 0. I mean it's not that we are applying any common mode inputs, but common mode inputs are also 0. Individually the differential inputs are 0 at both the inputs. When you do that, VO2 and VO1 will also come to 0. Right? So see here, if I apply 0 input at this terminal, I have grounded this, and I have also grounded this terminal. If I ground both these terminals, then VO1 will also come to 0, VO2 will also come to 0. So that's what I've shown here. Both these are at ground. So now R3 and R4 will appear in parallel. So if R3 and R4 appears in parallel at the non-inverting terminal, V offset I have modeled it as in series with it. Okay, so that's why I've written R3 and R4 parallel, and I've assumed this node to be ground because we have assumed zero input differential voltage. Okay, so that's why there is no excitation at the input, so the output voltages must also be zero for the first stage. Now if I assume only VOS3 is present, therefore there is no input current drawn, so there will be no drop across R3 and R4. VOS3 will just see a direct non-inverting amplification. So this part of the amplifier looks like a non-inverting amplifier with a gain of 1 plus R4 by R3. This is nothing but VOS3 times 1 plus G2. That's the offset voltage due to the input offset voltage of the second stage op amp. Now if I include the bias currents, IB3 plus and IB3 minus, then I'll have to figure out, so I'll just club these two resistors R3 and R4 and write them as a single resistor whose value is R3 parallel R4. Okay, so now you have a current IB plus flowing into the non-inverting terminal and IB minus here. So if you see this, yeah, so the IB minus current flows through this because I can argue that this node voltage, if you apply principle of superposition, you can find it out, but let's do that step by step. So let's assume there is only IB plus present, then the voltage appearing across the input of the second stage op amp, the second stage op amp will be minus of IB plus times R3 parallel R4. Okay, this will see an amplification of 1 plus R4 by R3. Okay, that's the non-inverting amplification due to this op amp. So if you multiply that, finally you will get, this is IB3, you will get minus of IB3 plus times R4. So that's what you will end up getting if you multiply these terms. I mean the IB3 into, if you expand R3 parallel R4, then multiply it with 1 plus R4 by R3, you will get IB3 times R4. Okay, now we'll analyze the impact of inverting terminal. So this current is now 0. So if this current is 0, this node voltage will be at 0 volts. This node will be at 0 volts. So no current will flow through the resistor R3. So all the bias current at the inverting terminal will flow through only R4. So V0 in that case will be IB minus IB3 minus times R4. So that's what I've written here. IB3 minus R4 minus IB3 times R4. So the total current at the output, the total offset voltage will be IB3 minus IB3 plus into R4. If you guys recall, we introduced a term called input offset current for an op amp. So this is the input offset current IOS3 for the third op amp. Okay, I can express it in that term as well. So now the overall output offset voltage due to the second stage op amp is the input offset voltage of the op amp times 1 plus G2 plus the input offset current times the resistor feedback resistor R4. So now that we have analyzed the output offset voltage due to the op amp non-idealities, we can combine all the results that we have done so far, derived so far, and write the overall expression. So if you write the overall expression, you get this term here. This term due to the input offset voltages and bias currents of the first stage op amps, the op amps A1 and A2, and the second term denotes the offset voltages due to the second stage op amps bias currents and input bias currents and offset voltages. So if I want to find the input differential offset voltage, I mean the input referred offset voltage, all I need to do is just divide it by G. That's the gain of, this is the output offset voltage. To find the input referred offset voltage, I just have to divide it by the gain of the different instrumentation amplifier. So if I divide it by the gain, I'll end up with this expression. VOS2 minus V. See, this term comes out as it is because it's getting multiplied by gain. So when you divide it by gain, it will appear as it is. Plus IB1 minus IB2 plus times RS by 2, and this is the difference in the base currents flowing into the inverting terminals of the first two op amps, multiplied by RF divided by G1. G1 is the first stage gain. The second stage offsets, the offsets due to the input offset voltage of the second stage and the input offset current of the second stage, their contributions get directly divided by the first stage gain G, the overall amplifier gain G. Generally, we know that the first stage gain is much greater than G2. That holds true in most of the instrumentation amplifier applications, and we also saw this information from data sheets. Whenever we want to program the gain, we normally program the gain of the first stage. Okay, and also we normally vary the resistance R. The first stage gain G1 is given by 1 plus 2 RF by R. Okay, so it's given by 1 plus 2 RF by R, and if I want to vary the gain, we normally vary this resistor R. RF is not touched. We leave RF untouched. So assuming G1 is much greater than G2, I can ignore, since G itself is very high, G is a product of G1 and G2. Okay, the gain itself is very high, I can ignore these two terms. So the offset due to the second stage can be ignored when you refer it to the input. And even the offsets due to the bias currents flowing into the inverting terminals, that can also be ignored, assuming because we are going to have for a given RF value of RF, we are going to achieve high gains by decreasing R, the value of R. So assuming G1 is really high, I can to a first order. If you guys recall, what does your G1 depend upon? G1 depends upon 1 plus 2 RF by R. Let's assume 2 RF by R is much greater than 1. If you have gains in the order of 1000, which will be very true. So this is 2 RF by R. So if you substitute G1 as 2 RF by R, you will end up getting this expression multiplied by, you will have this to be equal to IB2 minus IB1 minus times R. Yeah, so it will be times R by 2. This is what you will get. So it's getting multiplied by the feedback resistor, the resistor at the center, the programmable resistor value R. So if you want to have high gain, we normally choose this value of resistance R to be small. So this contribution also comes down. So finally, if I assume very high gain, I'll end up with the input offset voltages of the two op amps, the difference between the input offset voltages of the two op amps, and the difference between the input bias currents of the two op amps multiplied by RS by 2. So this is what your input differential offset voltage will be for an instrumentation amplifier. Okay, so all the op amps contribute to it. So it may be, the values may be slightly higher. See, remember the two op amps, the input offset voltages of the two op amps can be a little bit off. I mean, one can be positive, one can be negative. So I mean, don't think that they are two identical op amps, so offset voltages will be identical. That will not hold true, and the difference will, yeah. So if assume the two offset voltages are perfectly uncorrelated, two op amp offset voltages are uncorrelated, assuming that they are purely due to mismatches in fabrication, which is completely random, we can argue that the offset, since it's a random variable, depending on mean and variance, we can say its variance is root 2 times the nominal value. Assuming the variance of each of these op amps, the offset voltage variance of each of the op amp is some sigma, the variance will be root 2 times sigma. Okay, so that's the impact of offset voltages and how to find the input referred offset voltage of an instrumentation amplifier. And our conclusion from the discussion is it's mainly due to the input offset voltages of the first two op amps, the op amps in the fully differential stage. Okay, and also if you assume a finite source resistance, then the input bias currents will also add to the input offset voltage. Okay, thank you.